Hello? Is it on? I guess so. Okay, it's on, I guess. Let's start solving some problems. Let's go with something easy first because this is my first stream. Wait, hey, it's actually on. That's crazy. It's fucking crazy. It's fucking on. That's crazy, bro. That's so bored. So bored, bro. Okay. Okay, I know it's on now. Okay. Let's. Damn, I think it's lagging a bit. I feel like it's lagging, but I don't know. I don't know if it's lagging or not. Is my stream like on? I can try checking on my Switch account. Oh, okay, so this stream is good, but oh damn. I feel like I need to learn a lot more because, well, all the words are being cropped out. I need to edit. It's so annoying. Everything is being cropped out. That means I have to edit this. Maybe allow more space on the left. And then here I would put myself a little bit up. Not too sure. This definitely push this a little bit up here. Also means I have to a bit smaller and then extend like this. I don't even know. Okay, now it looks better. Looks a bit better now. Oh, the title is still there. Be better if I put it like this. Let's see. Mm, looking good, I guess. Now the problem setting. The problem set is and then now for the lower part. Where should I put myself? Probably here. No, no, it's a bit one to the left. Okay, looks good now, I guess. Wow, this setup is so interesting. Okay, it looks good now. Mm, okay, finally. Hello, can you guys hear me? Okay, I think you guys can hear me well and clear. Let's, I don't know. Let's continue solving the problem, I'd say. I don't even know, bro. Let's just solve some problems. It's already taking me too much time, like setting up all these things. Okay, tree matching. You're given a tree consisting of n nodes. A matching is a set of edges where each node is an endpoint of at most one edge. What is the maximum number of edges in a matching? Okay, so let's go into tree matching input. So here's the input for the problem. And the output is 2, expected output is 2. And now matching is a set of edges where each node is an endpoint of at most one edge. A matching is a set of edges. Each node is an endpoint. Maximum number of edges in a matching. What does it mean? What does it mean? Each node is an endpoint of at most one edge. So the current graph in the example is 1, 2, and then is 1, 3. So 1 connects to 3, and then 3 connects to 4, and 4 connects to 5. And the answer is 2. Answer is 2 because one possible matching is 1, 2, and the other one is 3, 4. I don't fucking understand. Hopefully cursing is okay on YouTube. Anyways, I don't understand. So 1, 2 means node 1 and node 2? Oh, it's 3, 4, 3, 5, not 3, 4, 4, 5. Okay. But I don't understand. A matching is a set of edges, where each node is an endpoint of at most one edge, but 3 is an endpoint of 2 edges. Maximum number of edges in matching. Oh, I understand now, okay. So 1, 2 is one edge, and 3, 4 is one edge. And those two edges don't share any common endpoints. Oh, okay. Okay, I see. Yeah. Okay, so for this problem, let's simply take n as the number of nodes first. Then we create a adjacency list. N plus 1, I equals 1, smaller than 2. N minus 1, I plus plus, u v adjacent u dot push back v. We're going to build an adjacency list based on the input. And then now, I think this is going to be a kind of like a DP problem. So we have these DP states. DPU0 means U is matched, is not matched. And DPU1, U is matched. When U is matched, we want to find a child node V such that DPV1 is, sorry, DPV0 is max. Because this child node is not matched yet, we'll match it with its parent node. This becomes 1. So if U is not matched, then we can plus other DPV1, I guess. dpv1 or dpv0. Okay, so for this dp, we are going to initialize the vector dp n+1, and then we have a function, a depth first search function. We're going to use depth first search in this problem. In depth first search equal u here, and then we are going to iterate over for auto v in adjacent u. So we are going to be children of u. So while iterating, we're going to save, let's save int cur, let's just make it cur 0. If it's not matched, oh, it should be a 2D array. Like this. And we would set dp dpu0 plus equal max of dpv. Let's do the search on b first, and then set dpv0, dpv1, dp. So if this is max, then this is min. dpv0 no, this should also be max. Let's canned equals 0, and then can equal max of canned max of dpv0, dpv1, and then plus dpv0 plus 1. Then dpu1 is the case when u is matched, is going to be equal to dpu0 plus 1, no shoot, dp, blah, 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 and we call Zephyr search on the parent. We're going to cout max of dp1 1 and dp1 0. So let's try to run this. Okay, let's check the output resolution. It's not outputting anything, which is strange. CNN adjacency list, iterate from 0 to n-1 for all the edges in the tree. UV, CN those, adjacency list pushback, get all the edges, for int U, plus equal max of dpv0, dpv1. Oh, the tree is undirected, okay. Push back U. Oh, so therefore we need a parent. Okay, we need a parent. Like this. VU 1 0. So if V is equal to parent, then we continue. I think this should be good. Oh wait, there's no return statement here? Wait, should there be a return statement? It doesn't have to, okay. Because we already saved all the states in the TP array. That Shouldn't be a return statement here because, okay, got it. And now let's check the output. Oh, the output is 2, which is convenient. It is our solution. Okay, let's try submitting it. Choose file. Choosing the main.cpp. Let's see. Okay, it is accepted. Cool. Okay, so what did we learn from this problem? The first thing is in DP, you need to store 2 states. The first state, when state is 0, it means the node is not chosen yet. And state 2 means the node is chosen. And we need to match the parent node with one of the child node which is not chosen. So that's why we're doing here dpu0 is equal to the max of 2 the choices of the children, because if the parent node is not chosen, then it doesn't matter at all. But when the parent node is chosen, then we need to minus the contribution of one of the best candidate by minusing the max gotten from here, and we add the contribution of that child node when it is equal to 0, when it hasn't been matched with any other node, and then we plus 1. We plus 1 because this current node U and node V will be chosen as a match, so then that's why we plus 1. Okay, pretty good. Let's move on to the next problem. Oh, but first we need to get commit tree matching, of course. Okay, let's move on to the next problem. Vector 03 tree diameter. And then we would create input oh wait, so here's the input, and let's start writing some code for the problem. You're given a tree consisting of n nodes. The diameter of a tree is the maximum distance between 2 nodes. Your task is to determine the diameter of the tree. So for this problem, what we can do is we can let's take n as the number of nodes in a tree, and then we would iterate over all of the edges in the tree. It will have n minus 1 edges. So we would initialize an adjacency list here. All of these are 1 index. So we would input take input u and v as 2 endpoints of an edge, and then we do adjacency list u dot push back v, and the other way u adjacency list B, push back U. After this, we would build like a depth first search function. Let's build depth first search function. What should this depth first search function return? I think it would return, sorry. So it would return the distance, the maximum distance, as well as the node and the node at that distance. So let's build a function void with has ints and ints as two parameters. Depth search function, then u and np, return void. And for this function, we would also iterate over all of the v children inside the adjacency list. If v is equal to p, we continue because it would be a parent. And if it's not, we would simply let's say here int cur is equal to 0. And we would have cur is equal to besides u and p, let's do another L, means the current layer. Int h1 and x1. h1 is equal to 0, x1 is equal to 0. Let's create an h. Then what we would do is we would save x equal to b, start u, and then h would be equal to L. Depth first search v u L plus 1. And then we would call this depth first search function. The parent node, the parent of that parent node, which is 0, and then the initial height, which is 0. And after that, we would have X and H saved. And I believe if we call depth search as X, and then P, I'd also call it 0, and L0 again, we would have H. I hope this is the correct solution. Let's try to run this solution. And let's check the output. Output is 3, which is good. And now let's submit the problem to see. Main.cpp. Okay, it is fully accepted. Cool. It's pretty easy. If you do this problem in this way, you depth search 2 times, it'd be easy. But I believe there's another way where you can do depth search like 1 time using DP. Oh boy, that would be a little bit harder, I'd say. A little bit harder. So if you do it that way, I think you would need to no. You need to divide into 2 cases, whether the current node is on the diameter or not. So I guess if you do it that way, let's see. There's a summation where I do it that way. Oh yes, yes I do it this way, I think. Priority queue for child in adjacency list. Okay. Priority queue dot push child to 1. It's not empty and I is smaller than 2. Okay. So it's taking the 2 maximum height of the child. And then do another depth search. Find a child. Okay. So there's 2 separate functions. The height depth search function only returns the height, and this depth search function it would return the like the diameter if the subtree is at the subtree with this node u as the node as the root node. But for this method, is there a scenario where no, there wouldn't be that scenario. Okay, that's a cool way to do it. Let's do tree distances 1. Okay, the solution for tree diameter has been pushed to GitHub. Let's move on to tree distances 1. Let's see. Let's create another directory, make for Let's go on to for input. Let's fucking oh, I cursed again, sorry. You're given a tree consisting of n nodes. Your task is to determine for each node the maximum distance to another node. Okay, this is interesting because the maximum distance to another node can be one of its child node, or it can go through its parent node. Okay, this sounds interesting. But for this problem, we can also, it is similar to tree diameter. We can also we can calculate the diameter first, and then the maximum distance from one node to another is actually the maximum distance to its diameter, to either end of the diameter. So okay, it's gonna be pretty interesting. Nonetheless, I don't know if I should do it in DP way or in the easier way. But let's try doing it in the hard way. So and vector adjacent n plus 1 and 0 n n plus 1 these, and then push back v jv dot push back u. Then we write a depth first search function. Then we have a dp function here. Present node u. returned. GPU1. Into and then at this we can iterate over for auto v inside adjacent seamless u. It is going to go. It's going to do. It's going to for auto v inside adjacent seamless u. If v is current, we continue. If not, then we dfs v. 23122. So the actual output is 23233. So for node 3, my answer is incorrect. Well, for node 3, it can go to 1 or to 4 or to 5. But, yeah, so the distance should be 2, right? Because 3 can go to 5. And so, let's say... What is wrong? What is wrong?